There appears to be something peculiar about this celestial visitor from another star system. China's Mars orbiter has recently transmitted images that defy conventional astronomical understanding. Following a passage near the Sun that resulted in a loss of over 13% of its mass, the object designated Oumuamua should have exhibited a substantial tail trailing behind it. Instead, all that is visible is a diffused sphere of light, devoid of any tail or dispersed debris. It is a scene of stillness where one would anticipate considerable activity. This is not an isolated anomaly. In fact, there are now 10 documented peculiarities surrounding this entity. 10 distinct behaviors that deviate from the predictable patterns observed in thousands of comets. Individually, each of these occurrences is rare. However, when all 10 are considered together, the probability of such a convergence drops to less than 1 in 10,000. While we are not asserting that this object is artificial, we are highlighting that something exceptionally unusual has traversed our solar system. And the more data we gather, the more perplexing the situation becomes. October 3, 2025. While the majority of Earth's population was preoccupied with other matters, China's Tianwen-1 probe, positioned in Martian orbit, was tracking a faint pinpoint of light. This spacecraft had been in orbit around the red planet for more than 4 years, its original mission having been completed long ago. However, this current observation was different. It represented humanity's most intimate encounter to date with an interstellar traveler. The object was moving at a velocity of 58 kilometers per second relative to the Sun, which equates to 129,000 miles per hour. At such a speed, one could circumnavigate Earth in just 18 minutes. The comet itself measured a mere 5.6 kilometers in diameter, roughly the width of Manhattan from river to river, and it was 18 million miles distant from the Tianwen-1's camera. Consider the magnitude of this observational challenge for a moment. The high-resolution imaging camera, originally designed to capture detailed images of Mars's surface from low orbit, had to be completely reconfigured. Instead of focusing on prominent planetary features from a close proximity, it was tasked with tracking an object smaller than a city, darker than asphalt, and traveling at speeds far exceeding anything typically encountered in our solar system, all from a distance of nearly 30 million kilometers. The Chinese National Space Administration refrained from announcing their attempt to observe this object until after they had achieved success. On November 5th, they released the captured images, monochrome frames depicting a hazy sphere surrounded by a diffuse halo. The coma, as they described it, extended for several thousand kilometers. They characterized this achievement as a significant technical accomplishment, a preliminary test for future deep space exploration endeavors. But here is what they did not emphasize, what truly imbues these images with historical significance. This was the closest any human spacecraft had ever come to Oumuamua. It was closer than the Hubble Space Telescope, closer than the James Webb Space Telescope, and closer than any terrestrial telescope could ever achieve. The European Space Agency's Mars Express and Trace Gas Orbiter also observed the comet during its close passage to Mars, but it was the Tianwen-1 probe that secured the sharpest images we are likely to ever possess. And these images revealed something unexpected, or rather, they revealed the absence of something anticipated. When a comet draws near the Sun, it experiences heating. Frozen volatiles, chemical compounds locked within ice for billions of years, abruptly vaporize. The solar wind and radiation pressure then propel this vaporized material away from the Sun, giving rise to the characteristic tail. The closer the approach to the Sun, the more pronounced the outgassing becomes, and the more spectacular the resultant tail. Oumuamua completed its perihelion passage on October 30th at a distance of 0.9 astronomical units from the Sun, a position closer than Earth and, at times, closer than Venus. NASA's Jet Propulsion Laboratory detected something remarkable within the trajectory data: non-gravitational acceleration. This indicated that the comet was being propelled by its own outgassing with a measurable force. The specific figures are as follows. At 1 astronomical unit from the Sun, Oumuamua experienced a radial acceleration of 1.1 times 10 to the -6th astronomical units per day squared, pushing it directly away from the Sun. Additionally, it exhibited a transverse acceleration of 3.7 times 10 to the -7th astronomical units per day squared, acting perpendicular to the Sun's direction. By applying the principle of momentum conservation, the calculations yield a definitive conclusion. To achieve this level of acceleration, Oumuamua must have lost at least 13% of its total mass during its closest approach to the Sun. 13%. This is not a gentle process of evaporation. It signifies intense outgassing. For an object estimated to have a mass of 30 billion tons, this implies the ejection of approximately 4 billion tons of material into space within a matter of days. 4 billion tons of gas and dust should, by all accounts, generate a breathtaking spectacle: a colossal coma, a prominent tail, and streaming debris visible for millions of kilometers. This is fundamental physics. It is the expected behavior of any comet that ventures this close to the Sun. So, where is it? On November 5th, 2 independent observatories captured images of Oumuamua following its perihelion passage. The Virtual Telescope project in Italy and the R Observatorio de Naves in Spain both released their photographs on the same day. Both presented the same observation: a compact, fuzzy sphere, a small coma, and no discernible tail. The Sun's position in these images is clearly indicated, as is the anti-solar direction, which is precisely where the tail should be, driven by solar radiation pressure and the solar wind. That is where the 4 billion tons of ejected material should be streaming away from the nucleus. Yet it is absent. Compare this to Comet Lemon, a typical solar system comet. The R Observatorio de Naves photographed Lemon just 2 days earlier, on November 3rd. The contrast is stark. Lemon possesses a clear, well-defined tail pointing directly away from the Sun, precisely as predicted. It appears as a comet should. Oumuamua does not. Now, before we proceed, let us consider the potential implications. Conventional explanations are currently under discussion. It is possible that the material ejected during perihelion consisted primarily of gas rather than dust, making it more difficult to detect. Perhaps the viewing geometry is misleading and we are observing the tail edge-on. It is also conceivable that the mass loss calculations are inaccurate and less material was actually ejected than the non-gravitational acceleration suggests. These are plausible hypotheses, and they are presently being investigated. However, here is the critical point. Each of these explanations necessitates a specific set of unique circumstances, and when one begins to accumulate multiple special conditions, when a series of improbable events must all occur simultaneously, that is when scientists begin to pay extremely close attention. Because Oumuamua is not anomalous in just this single aspect. The missing tail represents the 10th documented irregularity. There are 9 others, each independently perplexing and each requiring its own explanation. Let us examine them, not to sensationalize, but to gain a comprehensive understanding of what we are dealing with. Because, irrespective of whether this object is natural or not, it represents something entirely unprecedented, and the pattern emerging from the data is, at the very least, profoundly unusual. Anomaly 1. The trajectory. When Oumuamua was first detected on July 1st, astronomers immediately commenced calculating its orbital path. Within weeks, a significant characteristic became apparent. The comet's trajectory through our solar system aligned with the ecliptic plane to within 5 degrees. This may not seem particularly noteworthy, so allow me to elaborate on its significance. The ecliptic plane is the flat disk within which all the planets orbit the Sun. Earth, Mars, Jupiter, they all traverse their orbits in essentially the same plane, akin to marbles rolling around the edge of a dinner plate. This orbital alignment is logical, as they all originated from the same spinning disk of dust and gas, approximately 4.6 billion years ago. However, Oumuamua did not form within our solar system. It originated from interstellar space, where there is no inherent directional preference, no cosmic flat plane that dictates the paths of all stars. Interstellar objects are expected to arrive from random directions, from any angle relative to our solar system's orientation, from above, below, sideways, or diagonally. There is no inherent reason for them to align with our planetary disk. Yet, this object does. Its trajectory is retrograde, meaning it orbits in the opposite direction to the planets, but it does so almost perfectly within the same plane. The probability of this alignment occurring by chance is approximately 0.2%, or 1 in 500. This constitutes the first anomaly. Even before considering its composition or behavior, its path of arrival is already statistically anomalous. Anomaly 2. The sunward jet. Throughout July and August of 2025, multiple observatories captured an unprecedented phenomenon. Oumuamua was ejecting a jet of material directly towards the Sun, not away from it. This is contrary to expectations. Comets develop tails that point away from the Sun due to solar radiation pressure and the solar wind, which physically push ejected gas and dust outward. It is akin to attempting to blow smoke against a powerful fan. Physics fundamentally prevents material from streaming sunward against such pressure. There is a phenomenon known as an anti-tail, which is an optical illusion created by viewing geometry that can make a comet appear to have a spike pointing towards the Sun. However, this is not a real ejection of material. It is merely our perspective of observing the edge of a curved tail. Astronomers are adept at identifying these illusions, having witnessed them hundreds of times. The sunward jet emanating from Oumuamua was not an illusion. Multiple teams analyzed the geometry, meticulously checked the viewing angles, and performed rigorous calculations. This was indeed actual material being ejected towards the Sun, defying the radiation pressure that should have propelled it in the opposite direction. No conventional comet has ever exhibited this behavior, and no natural mechanism adequately explains it. Anomaly 3. The combination of mass and speed. Recall that Oumuamua possesses a nucleus approximately 5 to 6 kilometers in width, with an estimated mass of 30 billion tons. This is 1,000,000 times more massive than Oumuamua, the first interstellar object discovered in 2017, and 1,000 times more massive than Borisov, the second interstellar comet identified in 2019. Now, let us consider its speed. Oumuamua is traversing the solar system at a considerably higher velocity than both of these previous visitors, not merely marginally faster, but significantly so. Here is why this distinction is important. In interstellar space, larger objects are statistically less common than smaller ones. This is a fundamental principle of physics. There is more small debris than large celestial bodies. Similarly, fast-moving objects are rarer than slower ones because imparting high velocity requires a substantial expenditure of energy. The probability of detecting an interstellar object that is both exceptionally large and exceptionally fast is, according to statistical models, less than 0.1%, or 1 in 1,000. We have now observed 3 interstellar objects, and the third one happens to be 1,000 times more massive and moving faster than the others. While not impossible, this is a remarkably improbable occurrence. Anomaly 4. The timing of its arrival and planetary encounters. Oumuamua did not merely pass through our solar system, it made close approaches to multiple planets with remarkable precision in its timing. In September, it passed within tens of millions of kilometers of Mars, a time when the European Space Agency's orbiters were perfectly positioned to observe it. Subsequently, it swung past Venus, and then its trajectory brought it near Jupiter. Each of these encounters occurred at a distance close enough for detailed observation, yet not so close as to significantly alter the comet's trajectory. Furthermore, each encounter coincided with the presence and operational status of relevant spacecraft. And here is the particularly intriguing aspect. The arrival time was meticulously calibrated so that at perihelion, when the comet was closest to the Sun and potentially at its brightest, it was entirely unobservable from Earth. The Sun was positioned directly between us and the comet, rendering ground-based observation impossible. It is as if the object deliberately orchestrated a tour of the solar system's major observational platforms while simultaneously evading direct visibility from the planet, possessing the most advanced telescopic capabilities. The probability of this precise timing occurring naturally is 0.005%, or 5 in 100,000. Anomaly 5. The chemical composition. Upon initiation of spectroscopic analysis of the comet's coma, an unusual element immediately became apparent: nickel. It was present in significant quantities, exceeding the amount of iron, which is an exceptionally rare occurrence. In typical comets, if metals are present at all, iron is the dominant element. The ratio of nickel to iron has been well established through thousands of observations. However, Oumuamua reverses this ratio, exhibiting more nickel than iron, a pattern observed in industrially manufactured nickel alloys, not in natural celestial ice formations. Even more striking is the ratio of nickel to cyanide, which is orders of magnitude higher than in any known comet, including Borisov, the previous interstellar comet. Orders of magnitude signifies factors of 10, 100, or possibly even 1,000. This is not a minor deviation. It represents a fundamentally different chemical signature. The probability of a natural comet exhibiting this specific composition is estimated to be below 1%. Anomaly 6. The missing water. Comets are conventionally described as dirty snowballs, with water ice comprising their primary component, often accounting for 70 to 80% of their total mass. When they approach the Sun, this ice vaporizes, generating the characteristic coma and tail associated with comets. Oumuamua, however, contains only 4% water by mass. 4%. This is not characteristic of a comet. It contains barely any ice at all. It is more akin to a rock with a superficial dusting of frost. This finding contradicts our entire understanding of cometary formation. Whether within our solar system or any other, comets form in the frigid outer regions where water ice is abundant. There is no known formation mechanism that produces comet-sized objects with such a low water content. Yet, Oumuamua is classified as a comet because it does exhibit some outgassing. It is active. It is simply active in a manner inconsistent with typical comets. Anomaly 7. Extreme negative polarization. This aspect becomes somewhat technical, but it is crucial to understand. When light reflects off a surface, it becomes polarized, meaning the light waves align in specific directions. The degree and type of polarization provide information about the surface properties, particle size and shape, and composition. Every comet ever observed, including the interstellar comet Borisov, exhibits a consistent polarization signature. Scientists have developed models based on thousands of measurements, and these patterns are predictable. Oumuamua, however, displays extreme negative polarization, a phenomenon unprecedented in the entire database of cometary observations. This deviation is not slight. It is entirely outside the established parameters. The light reflecting from its surface is polarized in a manner that does not align with any models of natural dust grains. The probability of this occurring in a natural comet is estimated to be below 1%. Anomaly 8. The WOW signal alignment. In 1977, a radio telescope detected a powerful narrow-band signal emanating from space. It persisted for 72 seconds, was significantly stronger than background noise, and appeared to originate from the direction of the constellation Sagittarius. The astronomer reviewing the data was so astonished that he circled it and noted "wow" in the margin. The signal never repeated, and its origin remains unexplained. Oumuamua arrived from a region of the sky that aligns with the origin of the WOW signal to within 9 degrees. 9 degrees represents a relatively small area of the sky, approximately 18 times the apparent width of the full moon. Is this coincidence meaningful? Perhaps not. The precise source location of the WOW signal was never definitively pinpointed, and 9 degrees still encompasses a fairly substantial area. However, the probability of a coincidental alignment is 0.6%. Anomaly 9, the unprecedented brightness surge and color. Near its perihelion, Oumuamua experienced a surge in brightness that surpassed that of any comet recorded in the observational database. It did not merely brighten faster, it did so dramatically. The rate of brightening did not conform to any existing models of cometary outgassing. Furthermore, during this period of intense brightening, the comet appeared bluer than the sun. Normal comets reflect sunlight, thus appearing roughly the same color as the sun, perhaps slightly redder due to the presence of dust. Blue comets are extraordinarily rare, as there is no common mechanism that selectively scatters blue light more than red light in typical dust grains. Whatever was causing Oumuamua to brighten was also simultaneously causing it to emit or reflect an unusual spectrum of light: blue, intensely bright, and rapidly changing. And now, Anomaly 10, the missing tail despite substantial mass loss. This brings us back to our initial observation. The non-gravitational acceleration provides clear evidence of significant mass loss. The physics involved is unambiguous, and the mathematical calculations are straightforward. 4 billion tons of material were ejected from the comet's surface within a matter of days. Where did it go? If it formed a typical dust tail, we would be able to observe it. If it formed a gas tail, spectroscopic observations would have detected its presence. If it fragmented into larger pieces, tracking systems would have identified those fragments. Instead, we see a compact coma and no discernible tail, as if the ejected mass has simply vanished. Now, let us be absolutely clear about one thing. Each of these anomalies, when considered individually, possesses potential conventional explanations. Perhaps the trajectory alignment is merely a matter of luck. Maybe the sunward jet was a transient rotational effect. It is possible that the composition reflects an unusual formation environment within another star system. The absence of a visible tail could be an observational limitation. However, here is where the situation becomes unsettling. These are not isolated anomalies. They are 10 simultaneous anomalies occurring in the same object, and when one multiplies the probabilities, when one considers the chances that all 10 of these unlikely events would converge in a single comet, the resulting numbers become exceedingly small, less than 1 in 10,000, and possibly even less than 1 in 100,000, depending on the statistical models employed. This is precisely what Harvard astrophysicist Avi Loeb has been emphasizing in his recent analyses. Loeb is recognized for his unconventional hypotheses. He previously suggested that Oumuamua might be artificial. While many of his colleagues disagreed, his analytical methodology is considered sound. When an object exhibits multiple independent anomalies, each improbable in its own right, the emergent pattern cannot be disregarded. Loeb is not claiming that Oumuamua is a spacecraft, nor is he asserting it is alien technology. He is stating that the available data does not align with established models of natural comets, and this discrepancy warrants serious investigation. He advocates for increased observation, further analysis, and greater attention to the details that do not readily add up. And he is no longer alone in this perspective. The observational data is publicly accessible, allowing other researchers to conduct their own analyses. Some concur with Loeb's interpretations, while others do not. However, there is universal agreement that the object is highly unusual. So, what precisely are we observing here? What are the plausible explanations? The conventional explanation remains the most probable. Oumuamua is a natural comet originating from another star system, formed under conditions distinct from those in our own solar system and exhibiting behaviors we have not previously witnessed simply because we have never encountered an object quite like it. It is conceivable that it formed around a star with a different chemical composition, accounting for the anomalous nickel-to-iron ratio. Its parent system may have possessed different temperatures and pressures in its cometary formation regions, explaining the low water content. It is also possible that we are witnessing natural phenomena pushed to their statistical extremes, all coincidentally converging in a single object. This is the stance held by the majority of scientists, and it is not an unreasonable position. The universe is vast, and statistical outliers are inevitable. We have only observed 3 interstellar objects thus far, rendering our sample size exceedingly small. It would be premature to draw extraordinary conclusions based on such limited data. However, there exists another possibility, one that is more challenging to discuss within scientific discourse without risking dismissal, yet one that the data consistently suggests we consider. What if Oumuamua is not entirely natural? Not necessarily a spacecraft or a probe in the conventional science fiction sense, but rather something designed, something directed, something that serves a purpose beyond mere random wandering through the cosmos. Consider its trajectory once more. It entered our solar system aligned with the ecliptic plane, passed in proximity to Mars when multiple spacecraft were operational, swung past Venus, and approached Jupiter, all while remaining concealed from Earth-based observation during its perihelion passage. This could be interpreted as either an extraordinary coincidence or an intentional navigation. Consider its composition. More nickel than iron, and orders of magnitude more nickel relative to cyanide than any natural comet. Nickel alloys are utilized in spacecraft construction due to their inherent strength and resistance to heat. Is this significant? Perhaps not, but it is a noteworthy observation. Consider its water content. 4% water by mass makes this object resemble an asteroid more than a comet. Asteroids are denser, harder, and more durable. Should you endeavor to dispatch an item on an odyssey spanning millennia across the cosmos, would your construction material be of ephemeral ice, prone to sublimation, or of resilient rock and metal, built to endure? Consider the solarward outflow, matter propelled toward the sun against the relentless pressure of radiation, with no evident mechanism to account for it. Unless the underlying process isn't mere outgassing, unless it's something more, something actively driven. Reflect upon the non-gravitational acceleration, devoid of any observable tail. The celestial body is being propelled by an unseen force. We can quantify the exertion, yet the source of this force remains elusive. 4 billion tons of material have vanished, yet no debris field is apparent. Where did it dissipate? Now, I am not asserting that any of this definitively proves an artificial genesis. I am positing that the observed pattern is sufficiently peculiar that we should not readily dismiss the inquiry. Scientific advancement is predicated upon posing challenging questions, upon entertaining hypotheses that appear improbable until the evidence compels us to seriously consider them. Avi has encountered considerable critique for his readiness to explore these hypotheses. Some peers characterize his approach as sensationalist, suggesting he risks undermining his professional standing by contemplating the possibility that interstellar objects might be other than naturally occurring phenomena. However, Lowe's response is straightforward. The data is as it is. If 10 distinct anomalies manifest in the same entity, that constitutes observation, not sensationalism. And recently, an intriguing development occurred. Lowe received electronic correspondence from Chile, originating from an electrical engineer named Dario Villan. Villan conveyed his gratitude not for being factually correct or incorrect regarding 3I Atlas, but for rendering the subject accessible, for igniting curiosity in individuals who never imagined they would engage with astrophysics, causing them to suddenly pay heed. Villan shared an anecdote about his 18-year-old daughter, who had been uncertain about her vocational trajectory. She is now contemplating a career in astrophysics, influenced by Lowe's analyses of 3 Atlas, which presented the discipline as dynamic, uncertain, and brimming with genuine enigmas rather than firmly established truths. This is the inherent value of such junctures. Not the ultimate determination of whether 3 Atlas is natural or engineered, but the reaffirmation that our knowledge is incomplete. The universe continues to surprise us. There remain objects that defy our current understanding, and that is an exhilarating prospect. Currently, 3I Atlas is receding from the Sun at a velocity exceeding 200,000 kilometers per hour. By December 19th, it will traverse a distance of approximately 270 million kilometers from Earth, a gulf roughly 700 times the span between our planet and its moon. For a fleeting duration, humanity's most potent observational instruments will have a final opportunity for detailed study. Following this, it will recede beyond our reach. By January 2026, 3E Atlas will have completely exited our solar system. It will re-enter the vast expanse of interstellar space, journeying at speeds that will propel it light-years distant within mere decades. We will never again witness its passage. No subsequent generation will be afforded another glimpse. This was our singular chance. The data we have meticulously gathered will undergo scrutiny for years to come. New scholarly articles will be disseminated. Novel interpretations will emerge. Some scientists will contend that the anomalies are resolvable through conventional means. Others will persist in questioning whether we are overlooking a fundamental aspect of this object's true nature. Yet, a more profound question lies at the heart of this matter, one that transcends the specifics of 3 Atlas. It pertains to our fundamental approach to the unknown. For the majority of human history, we operated under the assumption that Earth occupied the central position in all things. Subsequently, we learned that we orbit the Sun, not the reverse. We presumed our Sun to be unique. Then we discovered billions of other stellar bodies. We posited that planets were a rarity. Subsequently, we identified thousands of exoplanets. We once considered interstellar objects to be theoretical curiosities. Then we detected 3 within an 8-year span. Each instance where we presumed the universe operated according to a singular paradigm, we were compelled to broaden our perspective. And each such expansion has been a lesson in humility. Thus, when an entity emerges from a distant star system, exhibiting 10 distinct anomalies, each improbable in isolation, all present simultaneously. What should our reaction be? Should we endeavor to fit it into established models out of intellectual comfort? Or should we acknowledge the possibility that perhaps the universe has revealed something we currently lack the framework to comprehend? I am not advocating for the endorsement of extraterrestrial artifacts. I am advocating for intellectual integrity. The information gleaned from 3i Atlas is peculiar. This is not subjective opinion, it is empirical measurement. Numerous independent research groups have corroborated the anomalies. The numerical data is publicly accessible. Anyone can verify it. How we process this peculiarity, how we interpret it, that is where discourse commences, and it is a salutary discourse. Science is not about attaining a consensus. It is about evidence, rigorous analysis, and the readiness to adjust our understanding when the data dictates such a revision. Here is what we definitively know. 3 Atlas stands as the most substantial interstellar entity ever detected. Its velocity surpasses that of its predecessors. Its chemical makeup is unlike any known comet. Its trajectory through our solar system presented an improbably opportune alignment for observation. It exhibited a sunward emission that challenges conventional physics. It shed at least 13% of its mass at perihelion, yet displays no commensurate tail. Here is what remains unknown: the underlying reasons for these phenomena. We possess hypotheses, some more conventional than others, but no definitive explanations. And that is acceptable. That is the very domain of scientific inquiry, the interstice between observation and comprehension. That is the crucible of discovery. The images of Tianwen-1, released on November 5th, will be subjected to prolonged study. Those indistinct monochrome frames, captured from Martian orbit at a distance of 18 million miles, represent humanity's closest ever observation of this object. Future investigators will enhance them, analyze them, compare them with other data sets, seeking details we overlooked on the initial examination. Perhaps those details will resolve the anomalies. Perhaps they will deepen the enigma. Regardless, they hold significance because 3 Atlas is not the final interstellar object we will detect. It is the third in a succession. As our detection capabilities advance and our telescopes grow more sensitive, we will identify more of these celestial voyagers traversing our cosmic vicinity. Each will impart knowledge. Each will challenge our preconceptions in distinct ways. And eventually, perhaps within our lifetimes, or in the lifetimes of the next generation of astronomers, we will comprehend the true nature of these entities. Are they cosmic detritus? Random fragments ejected from other star systems through gravitational interactions, drifting aimlessly through the galaxy? Or are they something else, something purposeful? Messages in bottles cast upon the interstellar sea, awaiting discovery? We do not yet know. But this is what renders this epoch historically significant. We are finally in a position to pose the question with seriousness. We possess the technological means to detect these objects. We have the instruments to analyze them. We possess the mathematical frameworks to compute probabilities and assess anomalies. For the first time in human history, we can do more than merely conjecture about our solitude in the universe. We can gather empirical data. We can conduct measurements. We can test hypotheses. 3. Atlas may not provide the definitive answer. It may remain an enigma, a captivating puzzle rather than a clear revelation. However, it has propelled the conversation forward. It has demonstrated that interstellar objects are more intricate, more varied, more surprising than we had anticipated, and it has served as a reminder that the universe is not obligated to conform to our expectations. It simply exists as it is, and our mandate is to observe, to measure, to question, and to follow the evidence wherever it leads. even if that trajectory leads to uncomfortable territories, even if it challenges our assumptions about what is conceivable, even if it compels us to entertain explanations we would rather avoid, because that, fundamentally, is what science is. Not a compilation of settled facts, but the process of confronting the unknown with intellectual fortitude. The willingness to admit, "I do not know," when the data is ambiguous, and the determination to persevere in investigation until clarity emerges. Three-Eye Atlas has bestowed this opportunity upon us. It has presented something genuinely anomalous, something that resists easy categorization within existing frameworks. Whether this strangeness ultimately points to unconventional natural processes or something more profound, we cannot yet ascertain. However, this much we can definitively state. We have witnessed something extraordinary. We have documented it. We have measured it. We have preserved the data. And now we must coexist with this uncertainty, this productive discomfort of not knowing, until superior data or refined theories provide illumination. This is our current state in November 2025, observing an anomalous object as it departs our solar system, carrying with it more questions than answers, reminding us that the cosmos is far more peculiar and magnificent than our current models suggest. The object remains discernible through substantial telescopes, still traversing at 129,000 miles per hour, still accelerating back towards the interstellar void from which it originated. We have weeks, perhaps months, of observational time remaining. Certain teams continue to gather data, conduct analyses, and strive to extract every conceivable piece of information before it recedes into perpetual obscurity. What they discover may not resolve the ongoing debate. It may merely augment the existing quandaries, but that is perfectly acceptable. Questions are invaluable. They propel us onward. They maintain our intellectual honesty. They prevent us from becoming complacent in our understanding of reality. And here lies the truth that imbues this moment with such profound significance. We are experiencing the inception of interstellar object astronomy. Not its mature phase, but its genesis. Consider our position merely 8 years ago. Prior to Oumuamua, interstellar objects were purely theoretical constructs. We understood they must exist, having been ejected from other star systems and adrift within the galaxy. Yet, we had never directly observed one. We possessed no empirical data, no measurements, no comprehension of their actual appearance or behavior. Now, we have 3 such entities, 3 data points, where previously there were none, and each has deviated radically from our expectations. Oumuamua exhibited acceleration without visible outgassing, rotated in a manner inconsistent with any known object, and vanished before we could adequately study it. Boris presented a more conventional profile, appearing as a comet that indeed behaved like one, though even it contained unusual concentrations of carbon monoxide. And now, 3 Atlas, with its 10 documented anomalies and its indistinct imagery from Martian orbit. 3 objects, 3 enigmas, and we are merely at the beginning. The next generation of telescopes will possess enhanced sensitivity. The Vera Rubin Observatory, slated for imminent operational commencement, will survey the entirety of the visible sky on a nightly basis. It will detect fainter objects, more distant entities, and those traversing at angles that current surveys presently overlook. Conservative projections suggest that we might identify 1 interstellar object annually once the Rubin Observatory is fully functional. Optimistic estimates place this figure higher. This implies that within a decade we could possess a catalog of 10 or 20 interstellar objects. Within 2 decades, hundreds. Each a visitor from another star system, each bearing information regarding conditions that we cannot investigate through any other means. Because herein lies the remarkable aspect of interstellar objects. They are unsolicited samples from alien worlds. Not alien in the sense of biological or intelligent life, necessarily, but alien in the literal sense. Foreign, originating from elsewhere, formed under distinct conditions, shaped by divergent processes, and composed of materials that may not exist within our solar system. Every interstellar object serves as a messenger. It has traversed millions or billions of years to reach us, bearing the chemical imprint of its point of origin, the physical imprints of its journey. It carries the narrative of a star system we will never visit. And for a brief interval, as it passes through our immediate cosmic vicinity, we have the opportunity to decipher that narrative. 3 Atlas represents one chapter, a peculiar, perplexing, and provocative chapter that generates more questions than it resolves. However, it is not the concluding chapter. It is barely even the prologue. The data we accumulate now will inform our comprehension of future visitors. The anomalies we document will form the bedrock for novel theories. The questions we pose today will shape the research agendas of tomorrow. And eventually, as the collective sample size expands, discernible patterns will emerge. Perhaps we will discover that objects akin to 3 Atlas are commonplace, and that the initial 3 we detected were in fact unrepresentative outliers. Perhaps we will uncover the opposite scenario, where most interstellar travelers are unremarkable rocks and icy bodies, thereby rendering 3 Atlas even more exceptional by comparison. We do not yet know, but we will. That is the promise inherent in this nascent field of astronomy. We are not confined to speculating about what might exist beyond our reach. We are actively observing what is presently present, meticulously documenting it, quantitatively assessing it, and engaging in discourse about its implications. And occasionally, quite remarkably, the data will defy our expectations. It will reveal something we had not foreseen, something that our existing models struggle to readily explain, something that necessitates an expansion of our understanding of what is physically possible. 3 Atlas exemplifies such a surprise. Regardless of whether it ultimately proves to be an exotic natural phenomenon or something more, it has pushed the frontiers of our knowledge. It has prompted us to reevaluate assumptions we were not even aware we held. It has served as a potent reminder that the universe is under no obligation to conform to our conceptual frameworks. There is a profound humility in this realization, an acknowledgement that we are still novices, still learning the fundamental lexicon of cosmic phenomena, still constructing the theoretical architectures required to truly apprehend what we are observing. But this realization is also accompanied by a sense of exhilaration. Because if the universe can so thoroughly astonish us with merely 3 interstellar objects, imagine the insights we will gain from the subsequent 100. Envision the discoveries that await in the coming decade, the next generation, the next century. Somewhere within the vastness of interstellar space, another object is presently en route to our solar system. It may already have traversed Neptune's orbit, remaining undetected due to its faintness or its trajectory. It may not arrive for another 10 years, 50, or even 1,000, but it is coming. They are all coming. The galaxy is replete with these celestial wanderers, and a minuscule fraction of them pass through our immediate cosmic environment. Each arrival represents an opportunity, a chance to acquire new knowledge, a chance to test our theoretical constructs against empirical reality, a chance to experience astonishment. And perhaps, just perhaps, one of these entities will be so exceptionally unusual, so profoundly anomalous, that it compels us to confront a question we have been carefully avoiding for decades. Are we alone? This is the underlying current that permeates every discussion concerning 3 Atlas. Every analysis of its chemical composition, every calculation of its trajectory probabilities, every debate surrounding the missing tail. It is the question that resides in the unspoken thoughts of us all, yet most hesitate to articulate. Could this be evidence of something beyond the scope of natural processes? Could 10 simultaneous anomalies, each individually improbable, constitute a discernible signal rather than random noise? I am not asserting that this is the case. I am suggesting that we should maintain intellectual preparedness for the possibility that, at some point, one of these interstellar visitors may indeed prove to be artificial. A probe, a messenger, a piece of discarded technology, something deliberately constructed rather than passively formed through random collisions and gravitational influences. That moment may not occur within our lifetimes. It may never occur at all. The universe might be teeming with natural wonders and entirely devoid of artificial constructs, and that, in itself, would constitute a valid answer to the question of our cosmic solitude. However, if that day does arrive, if we do detect something unequivocally artificial traversing our solar system, the initial step will involve its recognition. And that recognition will stem from posing the appropriate inquiries, from developing the analytical tools necessary to differentiate between the artificial and the natural, from maintaining a willingness to consider explanations that initially seem outlandish until the accumulating evidence renders them essential. 3 Atlas may not be that specific object. In all probability, it is not. But it is equipping us with the methodology to observe, to analyze, and to contemplate interstellar visitors not merely as astronomical curiosities. It is training us for whatever may follow, because something inevitably will follow. Another object, another enigma, another data set that challenges our understanding, and then another and another. This represents the new standard in astronomical observation. Interstellar objects are no longer mere theoretical constructs. They are observable, measurable, and analyzable phenomena that we will encounter with increasing regularity throughout the remainder of human civilization. Our descendants will mature in an era where interstellar visitors are commonplace astronomical occurrences. They will encounter accounts of 3 Atlas in textbooks, view the Tianwen-1 imagery in museums, and learn about the 10 anomalies that ignited such extensive debate in 2025. And perhaps by then we will possess answers. Perhaps the mystery will be resolved, the anomalies elucidated, and the debate concluded. Or perhaps not. It is conceivable that 3 Atlas will persist as an unresolved puzzle, a cryptic enigma from the nascent stages of interstellar object astronomy. The peculiar comet that defied all conventional principles and vanished before we could fully comprehend it. In either scenario, its significance remains. It is significant that we documented its presence. It is significant that we posed the difficult questions. It is significant that we preserved the data for future analysis, because science is a cumulative endeavor. Every observation builds upon preceding observations. Every mystery that remains unsolved today evolves into a crucial clue for researchers decades hence. Armed with superior instrumentation and more comprehensive theoretical frameworks, the Tianwen-1 images, those indistinct monochrome frames depicting a fuzzy sphere lacking a tail, will be scrutinized by scientists yet to be born. They will enhance these images utilizing algorithms currently beyond our conception. They will cross-reference them with extensive databases containing hundreds of interstellar objects. They will discern patterns to which we are currently blind, and possibly they will unravel the enigma of what we witnessed during October and November of 2025. Possibly they will elucidate the reasons behind 3 Atlas's anomalous behavior. Why it exhibited such a multitude of peculiarities, why 4 billion tons of ejected material left no discernible trace. Until such clarity emerges, we must endure the uncertainty. We will continue to meticulously analyze the existing data. We will prepare for the arrival of the subsequent interstellar visitor, and we will remain cognizant that the universe is vast, ancient, and astonishingly peculiar, far exceeding our current capacity for comprehension. 3. Atlas originated from an unknown location, perhaps a star system hundreds of light-years distant, orbiting a sun we will never observe, formed from materials and under conditions that we can only infer. It journeyed for millennia through the void, enduring temperatures approaching absolute zero, navigating through radiation fields and gravitational wells, carrying with it the chemical signature of its genesis. And then, for a brief period of several months in 2025, it traversed our solar system. It passed in proximity to Mars, to Venus, and to Jupiter. It approached the Sun at a distance of 9/10 of an astronomical unit. It encountered extreme thermal stress, vigorous outgassing, and forces that would have annihilated most comets. It expended 13% of its mass within a span of days, and then it departed, accelerated by forces we measured but could not visually identify, hurtling back towards interstellar space at velocities that will propel it light-years away within our lifetimes. We were afforded a singular glimpse, a solitary opportunity. China's Tianwen-1 mission captured the most intimate images we will ever possess. Ground-based observatories documented its post-perihelion state. Spectroscopic analysis revealed its composition. Mathematicians meticulously calculated its trajectory and acceleration. And now it is concluded. 3 Atlas is receding. By the time you receive this message, it may have already passed beyond the orbit of Mars, continuing its outward trajectory, diminishing in brightness, and becoming progressively more challenging to observe with each passing day. In January 2026, it will cross the outer boundary of our solar system and return to the interstellar expanse. Its cosmic voyage will persist across the vast expanse of the galaxy, potentially for another 1,000,000 years, or perhaps even 1 billion, until some gravitational encounter redirects its trajectory, or a calamitous impact brings its existence to a definitive end. Nevertheless, the gathered information endures. The visual records, the precise measurements, the detailed spectroscopic analyses, and the meticulously calculated orbital paths, all of which have been faithfully preserved. This wealth of data remains accessible for prospective investigators to scrutinize, to challenge, and to reevaluate in the context of novel revelations. This is precisely the essence of scientific endeavor. We endeavor to meticulously document the cosmos to the greatest extent of our capabilities. We perform measurements with accuracy. We safeguard our collected data. We pose inquiries. We readily acknowledge when our knowledge is insufficient, and we steadfastly continue our quest for insight, maintaining our observations and persistently striving for comprehension. The 3I Atlas mission has unequivocally demonstrated that the universe continues to hold unforeseen wonders, that our current theoretical frameworks are incomplete, and that, even 8 years into the emerging field of interstellar object astronomy, we are still grappling with fundamental principles, frequently finding ourselves taken by surprise, and consistently encountering phenomena that were entirely beyond our predictions. And it is precisely in this state of exploration that we ought to be, situated at the forefront of understanding, diligently pushing boundaries, embracing the inherent ambiguity, and fueled by the allure of the unknown. For the alternative, a universe that we believe we have fully comprehended, where nothing astonishes us any longer, and where every celestial body conforms precisely to established classifications, would represent a considerably diminished cosmos, a far less captivating realm. The 3I Atlas probe has bestowed upon us something far more valuable. It has presented us with profound questions, genuine, substantial, and scientifically sound inquiries that will undoubtedly propel research endeavors for years to come. It has furnished us with data that challenges our deeply held assumptions. It has granted us a glimpse into the sheer magnitude of what remains for us to discover. And in doing so, it has served as a potent reminder of the fundamental motivation behind our gaze toward the heavens. We do not look skyward with the expectation of readily finding answers, but rather out of an insatiable curiosity about the questions themselves. We do not believe the universe is obligated to provide us with understanding, but rather that the very pursuit of knowledge is an intrinsic aspect of our humanity. Therefore, as the three-eye atlas gracefully recedes from our telescopic view, embarking once more upon its interstellar journey, we are left enriched with those very questions. 10 documented anomalies, a single enigmatic visitor, and the unwavering certainty that more are destined to appear. The subsequent chapter of this unfolding narrative is already being meticulously composed. Another interstellar object is already en route. It is already traversing the vast emptiness between stellar bodies. It is already carrying within it its own unique set of mysteries and unexpected phenomena. We are simply not yet aware of its presence, but we will be. We possess the necessary telescopes. We have the advanced instruments at our disposal. We are driven by an enduring curiosity and a resolute determination to continue our observation. And when that next celestial visitor makes its appearance, we will be fully prepared. We will meticulously document its characteristics. We will rigorously analyze its composition and behavior. We will pose the most challenging questions and will diligently preserve all collected data for subsequent generations to study, reinterpret, and comprehend in ways that currently elude our imagination. This is the profound promise of this new epoch in astronomical discovery. Not definitive answers, but rather a cascade of compelling questions, not absolute certainty, but an unending journey of discovery. Not the vanquishing of mystery, but the profound and exciting commencement of genuine understanding. The three-eye atlas was indeed peculiar, anomalous, unprecedented, and unequivocally, indisputably real. We were privileged to witness something truly extraordinary. We meticulously documented our observations, and now we advance, carrying those crucial questions with us, poised and ready for whatever the cosmos may present next. Because within this universe, within this galaxy, at this particular juncture in history, we have finally attained the capacity to perceive beyond the confines of our own solar system, to welcome visitors from distant stars, and to investigate materials and processes that are entirely absent from our immediate celestial neighborhood. And on occasion, these visitors will be unlike anything we have encountered before. They will invariably disrupt our established models. They will exhibit behaviors that defy our current explanations. They will compel us to broaden the scope of our conceptual frameworks. This is not an impediment. Rather, it represents a remarkable opportunity. Therefore, let us offer a toast to the three-eye atlas, the enigmatic sojourner from another star system, the celestial body that defied simple categorization as a comet, the object that inexplicably shed 13% of its mass without displaying any discernible tail, the anomaly that ignited 1,000 scientific debates and will undoubtedly fuel research for many decades to come. We will likely never observe it again, but its impact on our understanding will be indelible. And somewhere out there, within the immense and silent void separating the stars, another visitor is already making its way toward us. We will be vigilantly watching.